That means by using this advanced, magnetic link, we can generate single source to multiple sources. Right here, you see, and this is single input and multiple secondaries. And each secondary can generate its DC source. Just if we use the rectifier here, then AC to DC conversion, then we can have this DC. Similarly, the second winding can generate another DC source. The third one can generate another DC source. So this is the solution to generate single source, to generate multiple DC, multiple balanced DC sources from single source. And this is the concept. And to eliminate transformer from the network, from the wind turbine neckly, here you see no transformer, right? That means basically this module means this sort of things right here. Is module 1, that means it is actually this part, right? Module 2 means this one. Similarly, we can connect many more modules in cascade in nature, okay? And these are for phase A, phase B, phase C. That means three-phase converter we can design here. And this power can fit to the grid directly because it is already medium voltage, 11 or 33 kilovolt. And here, one thing that I want to mention, this high frequency magnetic link, it is a very, very small component because we know by increasing the frequency of magnetic circuit, we can increase the power density, right? So we usually use here around 10 kilohertz, frequency. So therefore, it is a very, very smaller in size. And also, no voltage step up or down here. Unity turns ratio, primary and secondaries, they are same number of turns. The function of this magnetic link to generate single source to multiple sources, and it actually provide isolation, you see. And then by cascading these voltages, then we can generate medium voltage, right? And also this magnetic link provide the isolation. Therefore, you see what we actually predicted, right? That means voltage step up and isolation. So therefore, this type of technology can provide isolation as well as voltage stepping up. So if we use this concept, then no need any line filter, no need any step up transformer. We can directly connect wind turbine to the medium voltage grid with this type of power electronics and magnetic things. Okay, so here, although in this topology can eliminate the line filter and the transformer, but it has still some limitation, like how much power it can handle. How much power? Because of this single magnetic link, then there is a power handling limitation. There's a limitation to handle the power. So maybe this topology is suitable for 500 kilowatt, but wind turbine, you see, nowadays industries are developing wind turbines with a rating of more than 10 kilowatt and 10 megawatt. So can we use this concept for those wind turbines? Of course, no, because of this single magnetic link. So then I already modified the concept to increase the power handling capacity. So here you can see I proposed this modular concept, and from this low voltage side, they are looks in parallel. They are connected in parallel, and each module having individual high frequency magnetic link, right? Each module having individual high frequency magnetic link. So that means each high frequency magnetic link now handling maybe just 100 or 200 kilowatt power. So, and those modules are connected just by connection. You see, just this three nut bolt connection. So you can easily increase or decrease the number of modules, right? Similar. So if something happen in any of these modules, then we can just replace quickly by removing or connecting those six nut and bolts or screws, just like that. So therefore, this topology can eliminate the problem, that means the limitation of power handling capacity, and also it can improve the reliability of the system as well, because it is fully modular, just card type. That means we can just replace the one card, then faulty part can be replaced very quickly. So therefore, it actually improved the reliability. Okay, so we already tested this type of technology in our laboratories, and we found very interesting results. And here you can see the output voltage waveform, three-phase output voltage waveform, and here the line current and the phase voltage, right? So, and also, if we look at the traditional PV power plants, what are the technologies people are using, industries are proposing for solar PV power plants? So concept is still they are using two-level inverter concept, and this two-level inverter, it has higher harmonics components. So therefore, they need filter circuit, right? LCL filter, heavy LCL filter we need, and also the switching frequency here is much higher. Due to this higher switching frequency, we need EMC filter as well, electromagnetic interference, right? To remove the high frequency components. That means we need this filter to remove those high frequency components. Otherwise, those high frequency may interfere with the other components of the circuit. Okay, in addition, in order to fit this power from these PV power plants or PV modules, we need step up, heavy and bulky step up transformer to fit that power to the medium voltage grid. So I already mentioned the problems or the issues associated with this type of heavy and bulky transformer and also line filters. So in order to replace that technology, that means uh, the direct connection, that means step-up transformer or line filter-less direct grid connection of solar PV arrays. And here you can see the concept or the technology that can actually offers the direct connection of PPRs to this medium voltage grid. Here you see the output voltage, and this topology also modular in nature, right? Module 1, module 2, module 3. And as I mentioned before, we need two things to be confirmed, right? One is voltage stepping off. Here voltage it is around 400 volts, right? But in order to connect to medium voltage grid, we need 1133 or up to 36 kilovolt medium voltage grid, right? So That means our converter should step up the voltage from low voltage to medium voltage and also provide the galvanic isolation. So galvanic isolation, this high frequency magnetic link can ensure those things, right? And you say the power handling capacity is not a problem here because by increasing the number of modules, we can increase the power handling capacity of this type of technology. And this technology also tested in the laboratories, and we also found very, very interesting results. And therefore, we are very actually excited to push this technology further, right? And in the beginning, I mentioned in the future, we need this type of things. I mean, uh, we need something such that we can simplify our network, right? So right side, that is actually our futuristic projection, or that our actually based on the ongoing demand or ongoing changes, we can predict this type of grid, right? So for this type of grid, what we can propose, that means what sort of technologies that we can introduce to make the overall network simpler and easy to control, right? So in this case, maybe we can think about, I mean, we can introduce technology, something like this. I mean, that figure you can see on this slide here. It's a single unit, but it has multiple functions, and it can interconnect many things. It can interconnect different type of sources, different type of loads, energy storage. It can connect with medium voltage grid. It can connect with low voltage grid. It can connect with DC bus or DC grid. It can connect with AC grid, right? And power can flow in any direction through this high frequency magnetic link. So this is just a hub, right? Energy hub. That means through this hub, power can flow in any direction, either medium voltage to low voltage side, or to this energy storage, or energy storage to high voltage side, or energy storage to low voltage side, right? Here you see, this is DC microgrid, this is AC microgrid, here DC bus, AC bus, right? And this is a single unit. So with this concept, we can see the single unit that can interconnect DC grid, that can interconnect AC grid, that can interconnect storage, that can interconnect electronic load, AC load, distributed renewable sources, that can connect medium voltage grid, low voltage grid. Everything can be connected or interconnected with this type of concept, right? So, and it is called transformer. We can say it is a transformer because you see this side is medium voltage side, and this side is low voltage side. So basically it can step up the voltage and step down the voltage. And also, as I mentioned before, this fuser transformer should have the capability to regenerate the waveform. That means all the power quality problems can be eliminated, right? So this one can do that job. Not only voltage step up or step down, not only isolation, I mean galvanic isolation, it can introduce those things as well. That means the power quality problems can be solved. And also, you see, it is based on electronic switches. So therefore, any fault, any grid problems can be, protected by this device, right? We don't need any extra protecting devices to protect this device because it has sensors. That sensor can sense how much current is carrying. If it is looks abnormal something, then we can just remove the gate pulses from the IGBTs, then it is just turned off. That current cannot flow through these devices. It is just disconnected. We don't need any isolator breaker, whatever we are using in the existing or traditional grid or network. And also the power flow control. We can select how much power we want to flow in which direction. We can change the power flow, right? But in the traditional system, the power flow, flow of current depends on the load or grid voltage, right? But we can force to do something else with this type of concept. That's why this type of concept can be, we can actually now think this type of concept to overcome those things. Okay, now question is here, you see, it is fully power electronic based. That means it requires hundreds of IGBT or or power electronic switches. So maybe now you may raise question. That means the cost, power handling capacity, also the other things as well. So this slide may help you to find your answer. That is, industries are now trying to introduce new semiconductor switches. For example, silicon carbide instead of silicon semiconductor. Silicon carbide are, are much smaller in size. Here you see, if we compare the silicon carbide with the silicon IGBT, then you see how small it is. And power voltage handling capacity is also much higher. Now it is with the 15 kilovolt. The IGBT, it can handle only 6.5 kilovolt. And also if we compare the loss, also much lower. So therefore, of course, we can think to develop this type of technology with the latest power electronic devices. Another important thing in this future transformer is high frequency magnetic link, right? So high frequency magnetic link, that is basically responsible for the overall conversion losses or overall system losses or conversion efficiency. So therefore, we have to have very careful to select the material, magnetic material to develop this high frequency magnetic link. So we already investigated and we found that amorphous and nanocrystalline are two magnetic materials recently introduced, and they are very suitable for these applications because their flux density is very high, and also their core loss, specific core loss is also very low. So we can use that those materials to develop this high frequency magnetic link.
Sorry to interrupt, Professor Rabiul Islam.
Yeah.
Actually, our session time is actually going to end at 12:30 our time. So,
okay.
And also